seeking integers x and y, and it should be clear from the context that x is going to be an integer, but it's not going to be just a number. It's going to be some function of this variable s. Okay. And again, we have a polynomial in s on the right-hand side, and then the difference of two squares on the left-hand side. And also y has to be some function of s. I'll call it g of s if you want this time. Again, that's pretty clear in context, but sometimes it might be confusing, the notation where I'm saying find x and y a member of z. You may be thinking just real numbers like 8, 10, 11, and something like that. But we can't possibly find actual numbers here since the right-hand side is in terms of the variable s. So that's what we're seeking. Now, also an important thing to notice here, this looks impossible, but once you notice that this is the same thing as the binomial expansion here of s plus 4 cubed. And that's not too hard to verify, folks. Just remember when you cube something, that the coefficient pattern is 1, 3, 3, 1. You know, 1, 3, 3, and 1 would be the Pascal's triangle row for something raised to the third power. So you can see how 3 times 4 and 3 times 16 would give you the 48. Okay, now it turns out to be much easier to work in this form right here, x squared minus y squared is equal to s plus 4 cubed. And most of the work has already been done down here. Now, what I've done right here is just taken advantage of the very simple exponential truth that s plus 4 cubed is equal to s plus 4 quantity squared times s plus 4. Okay. Very simple stuff at this level. Much easier to handle it at this level rather than dealing with this third degree polynomial. Okay, so you see that's exactly where this s plus 4 squared came from, and then the s plus 4 right here. This comes from this straightforward, very elementary factorization. Now, if you add these two equations together, notice how these y's will cancel. This y will cancel with its additive inverse. And we end up with this statement right here, 2x is equal to, and you guys can follow this through. It really is fairly straightforward arithmetic right here. This step right here is after you factor an s plus 4 out, you will have a 1 left that will add to the 4 to give you the 5. And again, you guys can go through that step, but just factor s plus 4 out, which is what we do right here. And so you have one extra copy of s plus 4, so that makes it s plus 5 over here. Okay, dividing by 2, we get this function of s. Okay, so we'll call this our function of s. And that x is an integer. Okay. Now, so that part of it is done. And now right here, it's very, very similar. We substitute what we got right here into the equation right up here. Guys, can you see how that happened right here? It's just a direct substitution of x into this spot. This x right here will go right here. It's a little easier to put it here. You can put it in both places. It's a little easier to solve it right here. Okay. And here's all the work that accompanies that. I did leave something out right here. This will end up being the same thing. When you do this simplification right here, you'll end up with s plus 4 times s plus 3 all over 2. And that's all over 2 right here. Okay. So again, another function of s. Okay, call this g of s if you want. So we've produced two different integers that are a function of an other integer, unknown integer. And that finishes what we were trying to prove. Okay, that does it as far as what we're trying to prove. But let's go ahead and work through a concrete example here with these formulas. Okay, let's go down. Now we have this formula here for x in terms of s. We have this formula right here for y in terms of s, right? So let's see if we can figure this out. So let's do something kind of simple here. S, kind of a sanity check right here. Let's do s equals 1. Okay. So s equals 1 will go in on the right-hand side. All right. Now, so for s equals 1, our formula for x would give us 5 times 6 over 2, right? 5 times 6 over 2, isn't that 15? Okay, so we'll get 15 squared right here. Okay. Okay, again, folks, and what did I do? I just took this s equals 1 and substituted it right here for our x variable. Okay. Now, for our y variable, we will have to substitute 1 right here in our expression for y. And you get 1 plus 4 is 5, times 4 is 20 divided by 2. That's 10, right? Minus 10 squared, okay? Okay. And y'all, this works for anything. It's kind of cool. It works for negative integers. It trivially works for 0. Okay, so this would be equal to 1. Again, we're putting 1 everywhere we see an s, plus 12, trivial evaluation, plus 48, plus 64. You know, what is this? This is 112 plus 13. That's equal to 125. See, so this does check. In other words, this is a question mark at this point, you know. Well, we're not really, you know, but we know it's true because of the algebra above. But you see 15 squared, this is 225 minus 100 here, right? So this is a verification for a simple substitution, okay? So anyway, I thought it was kind of fun in the sense that if you first look at this and you don't recognize that this is s plus 4 cubed, then it's a very difficult problem. In fact, I wouldn't have any idea where to begin. But once you recognize it, that it's s plus 4 quantity cubed, it reduces the computations immensely. And again, y'all let me know if you know a way to do it other than this, but I think the factoring is almost a requirement here. I'm not sure how in the world you would go about this unless you had a nice compact factoring expression like this. Okay, thanks for being.